Welcome back to the Deep Dive. Today, we're really getting into something fascinating at the forefront of AI. We're exploring the latest AI models, the ones that don't just spit out an answer, but actually show their work, so to speak.
Yeah.
Generate a whole thinking process.
Exactly. These are often called large reasoning models, or LRMs, and that explicit trace generation, that step-by-step process, is their defining feature. It's supposed to mimic, well, a more deliberate kind of problem solving.
And they have shown better results on some specific tests, right? Like
Yeah.
math or coding stuff.
They have, yes, some definite improvements on certain benchmarks. But the real question, and this is what we're digging into today, is how deep does that actually go? Is it genuine reasoning, robust capability, or is it maybe something else, something a bit more superficial?
Okay, and guiding us through this is a really interesting research paper. It's called The Illusion of Thinking, Understanding the Strengths and Limitations of Reasoning Models via the Lens of Problem Complexity. Published just recently, June 2025, from machine learning researchers Parshan Shojai, Iman Mirzada, Sami Bengio among the authors.
Yeah, it's a great paper because it really questions those benchmark results. It basically says, look, scores are up on some things, but we still don't really have a good handle on their fundamental abilities, how they scale, what their actual limits are. It's all still pretty unclear, insufficiently understood, as the paper puts it.
Right, so the promise is they're showing the steps, feels intuitive, maybe more trustworthy, and it helps on some problem. But you're saying the way we usually test them might be missing the point.
That's exactly what the paper argues. The standard approach, it points out a major weakness there. Usually we just look at the final answer. Did it get the math problem right? Did the code compile and run correctly? Yes or no, final answer accuracy.
And what's wrong with that? Seems straightforward.
Well, a couple of big things. First, data contamination is always lurking in the background. Did the model just memorize something similar from its training data? It's hard to rule out. But the bigger issue, the one this paper really dives into, is that checking only the final answer tells you absolutely nothing about the reasoning trace itself.
I see.
Was it logical? Did the steps actually make sense? Did step B follow from step A? Or did it just, stumble into the right answer after generating a bunch of nonsense? You just don't know.
You see the output, but not the quality of the journey.
Precisely. It tells you what it ended up with, not how or if the thinking was sound.
Okay, so if just checking the final answer on standard tests isn't enough to understand the quality of the reasoning, how did these researchers get around that? How did they try to get deeper?
They used a really systematic, quite clever method. Instead of those standard benchmarks, they built their own testing ground using controllable puzzle environments.
Controllable puzzles. Okay, what does that mean, and why is it helpful here?
Well, the beauty of these puzzles is that they let the researchers control the difficulty really precisely. They could dial up what they call compositional complexity.
Compositional complexity?
Yeah, think of it like maybe building with Lego. A simple task is snapping two bricks together. A complex one involves many bricks, specific connections, maybe building parts separately, then putting them together in the right order. The logic of connecting bricks is the same, but the number of steps, the dependencies, the overall structure, it's way more complex.
Ah, okay, so they can make it harder in very specific, measurable ways.
Exactly. They know precisely how many steps or dependencies a correct solution should take. And crucially, this lets them analyze not just the final answer,
But the entire reasoning trace the model produces along the way, step by step.
right, so they get this incredibly detailed view of how the model tries to think as the problems get harder and harder.
Okay, so they put these models through their paces with these custom-built, increasingly tricky puzzles.
Yeah.
What did they find? Were there surprises?
Oh, yeah. Some pretty stark findings. The first major one, these top-tier frontier LRMs, they hit a wall. A complete accuracy collapse once the puzzles got beyond a certain complexity level.
Wow, a complete collapse. Not just getting worse, but totally failing.
Totally failing. It wasn't like a gentle slope down. It was like falling off a cliff. Performance just plummeted.
So that's the illusion part, kicking in hard. Looks good on simpler stuff, but the foundation just isn't there for genuinely complex tasks, at least in this controlled setup.
That's a key piece of evidence for the illusion idea. Definitely. They can mimic the steps for a while, but then, poof. And it gets even weirder when you look at how much effort they seem to put in.
Okay. What do you mean by effort? Like how long the reasoning trace is?
Yeah, things like the length or complexity of the trace they generate or related computational measures. You'd expect naturally that as a problem gets harder, the model would try harder, right? Generate more steps, use more of its token budget.
Makes sense. More challenge, more work until you hit some limit.
That's the logical thought. But they found this really counterintuitive scaling limit. The model's effort did increase with complexity, but only up to a point. And then, as the problems got even harder, the effort actually started to decline, even though they still had plenty of room, like a budget for more output tokens to generate more steps.
Wait, hold on. The problems get harder, but the models generate less reasoning, even though they could generate more.
Exactly. It's wild, isn't it? It suggests they aren't just failing because they ran out of space or time allowed by the system. It's like they hit some kind of internal fundamental breakdown in handling that complexity. The problem becomes maybe incomprehensible to their process and they just generate less, even with capacity to spare.
That's fascinating. So it's not just a resource limit, it's something about the nature of their process breaking down.
It seems that way,
Uh,
which really speaks volumes about the limitations.
and the paper also compared these LRMs, the ones showing their work against standard LMs, the ones that just give the final answer, right? Using similar amounts of computational power.
Yep, they did that comparison to see, what does generating that trace actually do for performance across different difficulties. And they found basically three distinct performance regimes, or zones, depending on the puzzle complexity.
Okay, 3 zones. What are they?
So zone one, low complexity tasks. Here, maybe surprisingly, the standard models, the ones not generating the trace, actually did better.
Better. Why would showing your work make it worse?
The thinking is maybe it's just unnecessary overhead for simple problems, like writing a 5-paragraph essay on why 1 plus 1 = 2. It just adds complexity and potential failure points for no real gain.
Okay, makes sense.
Yeah.
So simple stuff, just give the answer. What's the second zone?
That's medium complexity tasks. And this is where the LRMs shine. Here, generating that explicit chain of thought, those intermediate steps, provided a clear advantage. They significantly outperformed the standard models.
Ah, so that's the sweet spot for the LRM approach, where
Yeah.
showing the work actually helps.
According to this study, yes. That's where the benefit really shows up. But then you get to the third regime,
Which is,
high complexity tasks. And here, both models just collapsed. The standard LLM failed, and the LRM, despite generating its trace, also failed completely.
so at the highest complexity, generating the steps didn't save the LRMs. They failed just like the standard models.
Exactly. Neither approach was good enough for those really hard puzzles in their setup, which reinforces that the limitation isn't just how they approach it, but a fundamental inability to handle that level of compositional complexity.
Right. Now, the really cool part of this study was analyzing the actual traces, the step-by-step reasoning. What did looking inside those steps tell them about why the models were failing? What were the technical weak points?
Yeah, digging into the traces was crucial. It showed how they were failing, not just that they were failing. They identified a few key technical limitations. First, they saw real problems with exact computation. Anything requiring precise calculation or symbol manipulation within the trace, the models often messed it up. Small errors that then cascaded.
Okay, so basic arithmetic or logic within the steps was unreliable.
Often, yes. Second, they found a striking failure to use explicit algorithms. Even when a puzzle had a clear structure that screamed for a specific algorithm, like, follow steps A, B, C, the models would often just kind of improvise rather than applying the clear, efficient method.
They didn't recognize or couldn't apply a systematic procedure.
Seems like it. And third, their reasoning was inconsistent. They might handle a logical step correctly in one puzzle, but then fail on a nearly identical step in a different puzzle with the same underlying logic. No consistency.
Wow. So, inaccurate calculation, ignoring optimal procedures, and being inconsistent. That paints a picture of something quite different from robust reasoning, doesn't it?
It really does. It suggests the reasoning process is brittle, prone to specific types of errors, and not reliably applying rules. The traces look like thinking, but under the hood, these fundamental technical issues become apparent when you push the complexity.
And the paper mentioned this is part of a bigger research conversation, right?
Yeah.
Other work is looking at similar issues.
Oh, absolutely. They cite other recent papers, like one on interleaved reasoning via reinforcement learning, maybe looking at making the trace generation more efficient, or another called GSM Symbolic, focused specifically on the limits of math reasoning in models. It just shows that the community knows these are challenges. Understanding these limitations, like the ones highlighted in The Illusion of Thinking, is a major focus right now. It's not an isolated finding.
Okay, let's try and wrap our heads around the key technical points from this deep dive. What should we really take away?
I think the main technical takeaways are these. LRMs, the ones generating steps, aren't a magic bullet. This research suggests they help in a medium complexity range, but that's about it. They hit these really fundamental technical walls. Problems with exact computation, a failure to use algorithms systematically, and inconsistency. That leads to that dramatic performance collapse at higher complexities. And maybe most crucially for anyone evaluating AI, just looking at the final answer isn't enough. It hides these critical weaknesses in the actual process. You need to look deeper.
So considering all that they can look like they're thinking, they pass some tests, but they have these deep flaws, inconsistency, lack of exactness, and collapse under pressure. What's the final thought for our listeners? How should this shape our view of their reasoning and where we trust them?
I think the big question it leaves us with is if the reasoning we see is often more like a sophisticated pattern matching that looks like logic, but it breaks down fundamentally under complexity and lacks core properties like exactness and algorithmic thinking. What does that mean for relying on it? It suggests we need to be really cautious, hyper aware of these specific technical limits, and maybe question tasks where we assume they have robust, human like, or even reliable computational reasoning. The illusion can be convincing, but this paper shows it's often just that, an illusion, especially when things get tough.
A really critical perspective to keep in mind. Thanks for joining us on this deep dive into the complex